Today we are going to discuss about the next chapter called kinematics of particles under the Newton's law of motions. I taught very clearly in the earlier classes what about the mechanism of rigid bodies. Under this we have classified into two categories. One is the statistics and other one is the dynamics. Again, dynamics has classified into two categories. One is kinematics, other is kinetics. Kinematics means we have to consider the forces, what are the forces are acting on the moving body. The kinetics is motion with considering forces. Without considering forces is kinematics, with considering forces is kinetics. In early classes, school days, they discuss about the equations of motion, that is v is equal to u plus at, v square is equal to e square plus 2as, s equal to ut plus half at square, where small u is initial velocity, capital B is velocity, final velocity, a is acceleration, t is time taken, and s equal to distance travelled. That is distance. You know what is momentum? Momentum is nothing but the quantity of motion possessed by a moving body is called momentum. That is capital M. Rotation is capital M. Capital M is equal to mass into velocity. And we are very familiar with that of the Newton's law of motions, the first law, second law, third law. But here we are going to discuss and derive these kinematics of particles with respect to that is on the basis of the second law of Newton's. The rate of change of momentum of a moving body is directly proportional to the impressed force and takes place in the direction of the force applied is the second law of motion. Now, that is the rate of change of momentum is equal to final momentum minus initial momentum. We derive it as m into v minus m into u, that is mass into velocity. So let me take out m into v minus u, that is change of velocities. So m into v minus u is the change of momentum. The rate of change of momentum, rate of change of is nothing but with respect to time we have to express. So that is equal to m into v minus u divided by t. We are very familiar where v minus u is equal to a, that is acceleration. Rate of change of velocity is called acceleration. So let me out m and you have derived as a. So m into a as rate of change of momentum. So what is D'Alembert's principle? D'Alembert's principle is an application of Newton's second law. You know, for static equilibrium, we are very familiar with that of the conditions of equilibrium, that is summation of all horizontal forces equal to 0, summation of all vertical forces equal to 0, and summation of all moment equal to 0. Similarly, here dynamic equilibrium, we arrived from the D'Alembert's principle, that is P is equal to ma. Let us consider this block. The force is applied on the block P in the diverse direction. So an imaginary force should be acted in the opposite direction of the force applied, that is ma. That ma is the imaginary force, that is called the inertia force. So let me write P is equal to ma, that is P minus ma is equal to 0, where ma is the imaginary force or inertia force or reverse effective force, which is always acting in the opposite direction of the motion. So the inertia force is called inertia force act always opposite direction of the motion of the body, like a frictional force.